All right. So, first of all, a wonderful good morning. And indeed, it is still the morning session at 11:40. That's, I believe, the most unfortunate time slot I've ever been to, because at this point in time, everybody's thinking about the lunch break. Now, I've done the most severe error any speaker can do. I've mentioned lunch. Now, nobody is listening to me anymore anyway. But let's talk a little bit about design patterns and some misconceptions that I found out about. So first, give me 1 minute, 30 seconds to quickly introduce myself. My name is Klaus Iglberger, and I'm doing a lot of C++ trainings, consultancy, etc. And I talk a lot about design patterns. I've even written a book about design patterns because, from my point of view, this is a totally underrepresented topic in the community. It may be old, but I do not think that it's out of date or not important anymore. So let's talk indeed about design patterns, but perhaps in this talk with a special twist. It's primarily about terminology, because I've seen the terms, the names of design pattern used for various things, not necessarily the right things. Okay, before we now go into the terminology, a quick reminder of what is a design pattern. So design pattern, first of all, has a name. Now, for this talk actually is the primary thing that I want to talk about, because this name already has a lot of weight. It carries meaning. It communicates an intention. Now, if I name a design pattern, you should already have a pretty good idea what I'm talking about. Design patterns generally aim at reducing dependencies, and therefore help us to manage our software, structure our software. And I usually do this by providing some sort of abstraction. Some sort of abstraction doesn't have to be a base class. It's perfectly okay to just have a pointer, function pointer included. Base classes, of course, templates, standard functions, std variant, all of this stuff. Any way to provide an abstraction. And last but not least, design patterns are not invented, they're usually discovered, which is a pretty interesting detail in the end. So usually you see that something's working for a couple of years, perhaps even see this in many places working, and so then you've found and discovered a design pattern. So now, for me today, it's primarily about the name, because terminology indeed matters. Terminology matters because this is the way we communicate about code. And so, a quote from Carola Lilienthal that, from my point of view, expresses exactly why we have patterns in the languages. The use of design patterns provides us in our daily lives with decisive speed advantages for understanding complex structures. This is also why patterns found their way into software development years ago. Consistently applied patterns help us deal with the complexity of source code. So for that reason, I actually hope that when I use the term builder, all of you pretty much have the same idea, realize the same intention. Also, if I use the term factory method, I hope that all of you have pretty much the same idea. That when I say this, we communicate about the same thing. When I say bridge, I also hope that you have the same idea in mind, the same dependency structure. And last but not least, when I say design pattern, I also hope that we pretty much communicate about the same thing. And that is the 4 terms that today I want to talk about a little bit. So let's start with builder, indeed. And I admit that initially when I planned this talk, I actually didn't think about this, but I changed my mind when a couple of months ago, somebody posted at LinkedIn a kind of a nice overview of design patterns. Now, the 18 of the most commonly used design patterns. Now, a quick reminder to some extent. You see on top, it also mentioned the builder design pattern. Then somebody in this thread asked, what is your favorite design pattern? And many people replied, 44, it's a reasonable number. And I was super surprised to find that many people replied with builder. I was surprised because I don't see a lot of builders nowadays, so I was curious, and I was asking. Many people here state that their favorite pattern is the builder pattern. This makes me curious. Which programming language do you use, and which builder do you refer to? A, the Gov builder pattern, or B, Joshua Bloch's builder pattern? Unfortunately, you see only 5 people replied, but at least these 5 answers consistently said that actually they were thinking about the B, Joshua Bloch's builder pattern. So if you've not heard about this, this is a pattern that was first described in the Effective Java book many, many years ago. Now, I don't want to present any Java code, so I translated this into modern C++ to give you a little bit of an example. So imagine we have some class, and some class very quickly translates into widget. So we have a widget with a constructor that takes a lot of parameters, a lot of them. So it doesn't have to be 5, could be even more. And of course, immediately you see that this style is already questionable. Many, many integers that could be confused and switched. It's a dangerous kind of interface. But also, many of these values might have defaults. So I might assume x and y to be 0 by default, but I just cannot omit them because they're the first 2 parameters. So how do I approach this problem in a safe way, such that this interface is easy to use correctly and hard to use incorrectly? Well, the first step definitely should always be, even independent of this pattern, is to have strong types for these parameters. So the x position might be represented with the type xpos, the y position with ypos, with height, title, etc., etc. It definitely is a first step, totally independent of anything that follows. Good. Now with this, we could actually, indeed, very easily overload the constructor. We could have 10 different constructors that just express all the variations of parameters that we have. Okay. Not particularly convenient. So now that we have these strong types, what you can provide are set functions. So set functions for the xpos, the ypos, etc., etc. Note in particular that these functions are all called set, not set xpos, set ypos. No. All of them are called set, so we're consistently using function overloading here. And that is the key now. The constructor is now replaced with a very generic constructor that takes just arguments, Verdict template parameters. These arguments are all moved or forwarded, whatever, into the set function. And today we can very easily and conveniently do this by means of fold expressions. Very nice. All of these arguments are given to set, which of course, because of the strong types, calls the right set function. This is nice. Super convenient on the one hand side, and it certainly enables us to provide an interface that pretty much cannot be misused. So in the main function, we can pretty much pass all the parameters, but suddenly we have the ability just to omit a few, the ones that we do not want to specify, the ones where we want to use a default. And also the order certainly doesn't matter. We can first provide with or xpass or this way. Nice. Really nice. Pretty cool, amazing way to write a constructor that deals with a lot of defaults. And this is now what a lot of people think about when they think about builder. And if somebody asks the question, what is your favorite design pattern? This is what they think about. Unfortunately, this is not really what it is. This is not a design pattern. So to just go to the other pattern, the Gang of Four design pattern, here's a quick reminder of what the Gang of Four says about this. Separate the construction of a complex object from its representation so that the same construction process can create different representations. So of course, in this book, published in 1994, they use an inheritance hierarchy, which was just the thing of the time. Yeah, this was the 90s. Object-oriented programming was all the rage. But there's one thing about this picture, this is why I used it, which makes it clear that this is different. Implicitly, there is an architectural boundary in the middle. So I have a clear separation between two levels of programming, the abstract part on top and the more concrete part at the bottom. And so there is definitely an inversion of dependencies happening. I communicate by means of this inheritance hierarchy. Good. And so, yes, there are two different builders. There's first the Gang of Four design pattern, builder design pattern, and then there's Joshua Bloch's builder pattern. But I would clearly say that Joshua Bloch's builder is not a design pattern. Don't get me wrong, it's super valuable and absolutely cool. I would use it too, but it's not a design pattern. There is no architectural boundary. I do not really separate between two levels of code. That's not the intention. And so I'm definitely also not focused on reducing or inverting dependencies. It's just a very useful and very convenient implementation detail. But this is what it is. I would say that it's super similar to an API pattern called Fluent Interface. If you've not heard about this, please check it out at Wikipedia. Super simple to find because it is a pretty very common thing to write interfaces. Perhaps not so much in C++, I don't know. Other languages use this more often, but this is pretty much an ability, gives you the ability to write fluent code, things that you can pretty much read. It's like writing sentences in code, and so comprehensibility and usability, of course, should improve. Good stuff, just not a design pattern. So please don't confuse Joshua Bloch's builder pattern with a Gang of 4 builder pattern. They're two different things, which unfortunately have the same name, which of course now brings me back to the terms. It's a little difficult nowadays to talk about builder. Now somebody asks, what is your favorite design pattern? Some people say builder, and these two people might have very different things in mind. That's unfortunate. So if you today use the term builder from now on, it might not be a bad idea to be a little more specific. Do you talk about the Goff builder, Gang of 4, or do you talk about Bloch's builder? Yep, both have their values, both are superb. They're just very different things. All right, so terms matter, else we are talking about two completely different things. Which brings me to a second term. A term that, oh my, I've seen used so arbitrarily in so many blogs, books even, that by now I believe nobody really knows what a factory method is anymore. So, quick example, some toy example. We want to draw shapes. So to get started, I first have a vector of unique pointers of shape. And of course, it doesn't have to be, but that's the traditional thing, the classic thing again. And I abbreviate this with shapes. It's more convenient. Then there is a function that allows me to draw all the shapes. That's good. Yeah, convenient again. But then I have a function to read shapes from JSON. I pass a string, the file name, and I get all the shapes, everything that's stored in the JSON file. And then in the main function, I read the shapes from JSON and I draw them. Cool. Now, my major point of interest is the read shapes from JSON function. Now this function creates all the shapes. And so it creates something, it's a factory function. In literature, however, and as I said, also in blogs, etc., very often this is considered to be an example for the factory method design pattern. We create something. No. Unfortunately, no. A creation function is not automatically a factory method or not even a design pattern. Again, don't get me wrong, it's a valuable thing, but it has nothing to do with software design. So, again, don't get me wrong, this definitely improves code, without doubt. So, it encapsulates this creation process, super valuable, because now you can change things in one place, and that's one function. If a new kind of shape enters the picture, you can do this in this one function. You don't have to do all of the code base. And so on. You're in control to do things in one place. Fulfills kind of the SRP and dry. Good. But, again, we have not really thought about reducing any dependencies. So, if it's not dependency related, it's probably not a design pattern. It's merely an implementation detail. But then what is a factory method? Okay, let's use this example to just develop it into something where we actually talk about dependencies. So let's first introduce an architectural boundary. That's the first point, the starting point. But okay, again, we have high level low level. This is terms that usually confuse people. So let's make it a little more specific. The upper code is my code, and the lower code is your code. So you read shapes from JSON, and it's good for you, absolutely. This is valuable for you, but I don't care about this at all. It's a little implementation detail on your side of the architecture. I don't have to know this. But now let's make things more interesting. Let's just argue or assume that I want to create shapes too, but I don't really want to deal with the details. So in order to get an example, say I now need a create and draw shapes function. I want to create a couple of shapes, I want to draw them. And draw shapes is on my side. But not the read shapes from function, shapes from JSON function. That function is on your side. Now, if I would call this, actually it would totally break the architecture. You can use my code, but I cannot use your code. So this definitely is not working at all at this point. So consequently, I would have to take your function. I would have to become the owner of read shapes from JSON. But this makes both of us pretty unhappy. First, I now suddenly have to deal with all the shapes. Suddenly I know about circles and rectangles and squares and all these things that I don't really care about. And you cannot change my function. It's my function suddenly. You are no longer in charge of the details. That's bad. However, let's start to communicate. Let's start to design that. So our goal is that I can create shapes when I need them, but I definitely don't want to depend on all the details. That's your problem. And you actually want to depend on the details, but you might not be so much concerned in when and how to draw them. All right. So this is where this factory method design pattern enters the game. As a quick reminder, what does the Gang of Four say about this? Define an interface for creating an object, but let subclasses decide which class to instantiate. Factory method lets the class defer instantiation to subclasses. Of course, there's certain connotation here. It talks about subclasses, which is very object-oriented. But again, this is the time. This is just what the book does. It primarily talks about define an interface for creating. And this is now what we do. So first of all, you get your function back. I don't want to know the details. Okay. But then in my create and draw shapes, I just open up the world for your code by introducing a function pointer. Function pointer. Such an archaic thing. Okay. Doesn't have to, but then you totally lose the idea that it has to be a base class. So I take a function pointer to some function that creates shapes and just use it in my function. And really, I really don't care what I get. I can just use the stuff. You, on the other hand, okay, and this is now an example for the factory method design pattern. Yes. And note, I point to the function pointer. I do not point to the function below. The function below is still just an implementation detail, factory function. The factory method is actually just my function pointer. So you cannot just pass your function to my code. And that's great. Yeah, so suddenly I can create shapes without having to know the details. Good stuff. So again, the core of this entire idea is that there is an architectural boundary somewhere in the middle, and that there is a dependency inversion. Yeah, I talked a lot about dependencies. I talked a lot about I don't need to know this stuff. That's pretty much what the design patterns do. So just that some of you can sleep well, of course we could do this with a base class. Sure, we have a shapes factory on my side of the code with a virtual create function. I take a, say, reference to the shapes factory in my function, and you could implement this, of course, however you want to. But it's the same idea. It's not something totally different. It's not suddenly, now suddenly a design pattern. So the takeaway is that factory method and factory functions function are two different terms, which unfortunately are mixed up so often. The problem is that in C++ we often talk about methods. But to just say it clearly, in C++ there are no methods. Now take a look at the index of the C++ standard. The term method doesn't appear. There are no methods in C++. We have functions everywhere. And so factory method is kind of a special term, which indeed comes a little bit from the Java world. So this is actually something that's not just my idea. This is something that's even written at Wikipedia. So if you go to the English version, look for factory, and then go to terminology, then indeed, as the explicit statement, unfortunately this is not really visible here, the last sentence, the general concept of a factory is often confused with a specific factory method design pattern. Two different things, unfortunately. And so, remember that the term factory is heavily overloaded, and that factory alone does not necessarily refer to this factory method design pattern. So distinguish between the general idea of a factory function, and really you can use that term for anything. Anything that creates something is a factory function in the end. And distinguish to factory method. That's something that has a certain, carries a certain meaning. We somehow distinguish, communicate about how shapes are created. I want to do this, but you know the details. So perhaps consider factory method design pattern a customizable factory function. That might be a good translation. All right. There's another term that I would like to address. Bridge, aka the pimple idiom. I think when I say bridge, you already have a pretty good idea. But still, allow me to quickly give you a little bit of an motivation. So this time my motivation are electric cars. Why? Well, because I not just say that in electric cars things are changing a lot. In particular, the battery technology is changing a lot. So if you now consider this in terms of a class, some electric car class, then this class might have a data member called battery, of course. However, having this data member as a concrete type might actually create a lot of change indeed. So whenever something about battery changes, users of electric car will experience the change, will see this change. And if the size of battery, for instance, changes, it's not just some change. It really is an ABI break. Everything will have to be recompiled. Everything that uses electric car. So if this happens often, this might be a real inconvenience. And it might be something that might not be even acceptable to people. So what to do about this? Well, we could first of all, again, introduce some abstraction, some battery. Okay. Battery is a base class with some functions. Say charge, that should give you an idea. So then electric car. Electric car does no longer store battery as a concrete type, but as a pointer to base, as an abstraction. And we might get this via the constructor. Okay. Then of course there are many different implementations of battery. Battery Gen 1, Gen 2, Gen 3. Yeah. Things change. There's a lot of new stuff. And then in the electric car class, we would just get our battery. That is provided via the constructor. So electric car takes some battery, say battery Gen 1, and electric car does not change again and again and again anymore. Good. So electric car itself becomes pretty ABI stable. Again, this is, well, not exactly the example, but a very similar example to what we see in blocks and books even. This is not a bridge. Unfortunately, it pretty much sounds like a bridge, but it is not. And it is about this particular parameter. So we are injecting the battery Gen 1 into the electric car class. And yes, you know the term for that, dependency injection. Not to be confused with dependency inversion. That's something different, but we inject the battery. And so this is usually given as a bridge example. But say it clearly, bridge is never about dependency injection. Never was, never will be. That's not what bridges are about. To show why, let's indeed go into the example that the Gang of Four in their book give on their own. So we don't have to understand the complete example, just the upper setting. Their example is about windows. So we have different windows. The windows, however, depend on the platform. So we might be on Linux, we would use something different than on Windows, different than on Mac OS. So in order to factor this out, these differences, we introduce a window imp. Yeah, they call it imp, not impl. And this thing has many, many different implementations. Yeah, X window, Qt window, whatever is available. Good. But this is what they write about this particular example. Consider the implementation of a portable window abstraction and user interface toolkit. Clients should be able to create a window without committing to a concrete implementation. Only the window implementation should depend on the platform on which the application runs. So, not my words, their words, but pretty clear. Without committing to a concrete implementation, they should not depend on the platform. The code example, okay, this is really pretty much copy and paste from their code example, and no, that's not what we do today anymore. Please don't. But just to point it out in code, we have this window imp up here. That's the abstraction of different kinds of implementations, some pure virtual function, whatever. And we have the window class. This window class has a window imp. Yes, this is the thing that you please do not copy. Nowadays, a unique pointer is not just optional anymore. This window imp, that is my pointer to implementation. Now, we commonly call this pimple nowadays, not just imp. That is my pointer to implementation. But this pointer to implementation is not passed anywhere. No, this is my personal, private little thing that nobody else needs to care about. Problem about the example, however, is that in the constructor, I'm given a view. And this view is another data member. But this view has nothing to do with the bridge example. It just happens to be there because it probably feels a little more realistic. That's another design pattern. This is what we call the strategy design pattern. And that's the difference. Yeah, kind of combined in this example. The bridge pattern is not about injection. This is about hiding the details as much as possible. Yeah, you don't care, it's my concern. The strategy pattern, on the other hand, is very much about dependency injection. Yeah, this is exactly what the point is. You give me the view, and I don't need to care. So to just, and of course note, many people then just call things impl, and then it's a bridge, or pimple, or whatever. The name of the data member doesn't make a difference. It's about how you provide this impl. So our car example, in order to fix that, to really make it a bridge, we would not have to do a lot. The battery would still be the same, pretty much. The electric car class, however, would change a bit, because suddenly in the constructor, I would not accept an engine anymore. A battery anymore. That's my concern, not yours. Yeah, I deal with battery. Then, of course, no dependency injection. Then, of course, there are still many implementations. Yeah, but these implementations are chosen by the electric car itself. Electric car creates its own engine. And so if you create an electric car somewhere in the main function, for instance, you just, well, give it a name. Perhaps you give it some other things that are a little more superficial, but you do not care about batteries. That's entirely a problem of the electric car itself. So that's a bridge. So the confusion probably comes a little bit from this really big similarity. This is the UML class diagram that a Gang of Four uses. Kind of. I'm now using my example, but this is pretty much what it looks like. Yeah, there's a little box that says bridge. But if you then compare it to the strategy design pattern, it looks alike. It's the same UML class diagram, no difference at all, except for the little box that says bridge. And so it is easy to confuse. It is easy not to see the difference. But the difference becomes visible if you really think about dependencies. So this is the dependency structure of bridge. So on the left, lower left, the electric car directly uses the battery Gen 1 and Gen 2 and Gen 3. It directly uses that. So these two are on the same level of the architecture. They know each other. That's the point. Strategy, on the other hand, moves this battery Gen 1 to a lower level. So now the electric car is totally unaware of a battery and requests a battery in its constructor. Please give me a battery. Somebody else now takes care of that and provides this at another level of the architecture. So again, the difference is an architectural boundary. All right, so please do not confuse bridge and strategy. And if somebody in some code example explains bridge by dependency injection, please just rethink, say, okay, it's a strategy. So use the term bridge when you do refer to internal customization, no dependency injection. Again, that's the point of a bridge. And if there is a dependency injection, it's very likely a strategy. Not necessarily, but very likely in the example it definitely was. So bridge is about internal customization, strategy about external customization. All right, so again, the term matters, else we are talking about two totally different things. So which brings me to term number 4, the term design pattern. Now, sometimes Submit talks about design patterns in general, and one of the latest reviews I get back contained the following remark. I believe that object-oriented programming, especially its theory, is overestimated. C++ always had templates, and now it also has std variant, which makes most of the use of inheritance unnecessary. So the opinion itself, I feel, is deeply flawed. But there's something else now here. As soon as you say design pattern, people think about object-oriented programming. It's like a reaction. It's like, this is what it is. So design patterns equal object-oriented programming. Not really. Not really. And this is not news. Some of you might know this book, Modern C++ Design by Andrei Alexandrescu, who, by the way, is at this conference. And Andrei is still mocking the community by saying he invented modern C++. Because this book was published in 2001, so kind of 10 years before we had C++11 with modern C++. Okay, joke aside, in this book he uses design patterns. It's in the subtitle, but never by means of a base class, but very consistently by means of templates. At the time he was torturing compilers, everything was done in templates, and I think there was one compiler that could compile his code. So we have already learned that it's not just about base classes. So strategy. I just picked on this one because this is something quite useful to talk about. So this classic form is often considered to be the one implementation. Strategy is a base class, and we can provide things. Indeed, nothing could be farther from the truth. There's so many different ways to do a strategy. And in fact, the C++ standard library itself uses hundreds of strategies. Indeed, hundreds of them. So, just a few examples. Unique pointer. That's a class that all of us know about. And I think you are aware of the fact that unique pointer actually has two template parameters, T and the deleter. T being the type that we deal with, and deleter being the thing that cleans up eventually. Now this deleter, this is not just some nice new idea. This deleter is actually a strategy, just in template form. dependency injection. So we inject the deleting behavior into the unique pointer class. We configure the unique pointer. That's a strategy. Then stud vector, the container. Two template parameters again. We have the T and we have allocator. And of course, the allocator. It's not just some idea. It allows me to inject the allocation mechanism. It allows me to say, to tell vector how to acquire memory. It's a strategy again. Nothing but a strategy in form of a template parameter. In fact, pretty much all containers use a strategy all over the place. So hash set here actually has 3 different strategies. Then, algorithms accumulate. So I want to accumulate, meaning sum up, all the numbers in this vector of integers, 1, 2, 3, 4, 5 to 7. Of course, I would pass begin numbers and numbers as 0. Okay, and then I can decide how to add things up. Okay, I chose the boring thing perhaps, but stud plus. What is stud plus? Well, it's a strategy. It's a strategy. I inject the behavior for the accumulation into accumulate. I decide how accumulate should do its work. Accumulate doesn't care, it will do its job. I can inject this behavior. And next example, generate. So generate is the algorithm that builds a vector with numbers, not in the sense of it adds numbers, but it sets the numbers. Generate takes a, no, not a strategy, a factory method. So now, not every dependency injection now must be a strategy, but this one generates something. And again, it's a template parameter that allows me to say how the things, which things are created. Factory method. And so indeed, generate could be written in so many different ways. Of course, the standard way of doing things is to pass a template parameter, generator, and yes, of course, this is the right way of doing things. But it would still be a factory method if I would do this in form of a function pointer. Yeah, okay, the archaic thing, but I could do it if I wanted to. So function pointer, still factory method. I could, yes, of course, also use a base class. Not particularly good idea in the context of the STL, but generally it would be a factory method. So in form of a base class. And last but not least, I could envision also that we pass a stud function. Again, not a good idea. Suddenly we have runtime polymorphism, but it definitely is still a factory method. So it's not the how I implement it, it's what I want to express. It's the name, it's the term. So, my own quote, design patterns truly are everywhere. Every kind of dependency inversion, every kind of dependency management, all of these are design patterns. They are everywhere. We cannot work without them. So, please do not believe that design patterns are object-oriented programming. Now, I believe they're one of the most essential building blocks for successful software development. And as part of that, being such an essential building block, it definitely is about the terminology. So if we cannot talk about them because we misunderstand each other, because you have a different idea, then of course this doesn't work really well. So please realize that the terminology around design patterns represents an essential tool to deal with software complexity. And so, to quote Carola again, the use of design pattern provides us in our daily lives with decisive speed advantages for understanding complex structures. This is also why patterns found their way into software development years ago. Consistently applied patterns help us to deal with the complexity of source code. So, and as such, I really think that terminology truly matters. So please keep these terms in mind and use them consistently. Thank you very much. So we definitely have time for a few questions, if there are some. All right. That was the capital mistake. Okay.
One question. Wouldn't the example where you pass the generator argument to the argument of the factory to the generator, couldn't you interpret that also as a command?
Whew. And here we are again. So the question was, just to speak it out loud again, couldn't this injection of a pointer, etc., be a command? Oh my. This is now something we could talk for hours about. Yeah, command is again one of these patterns that looks exactly like strategy and factory. They all look alike at some point. So I would not fight over which term it truly is. Doesn't matter. The most important point is to really realize that there is some dependency management happening. So if you feel like it's a factory method, and if you call it this way, I called my function pointer factory method, okay, then you communicate what you want to have in code. If you call this command, okay, then why not? Then you interpret this as a command, still gives me the ability to do something. Yeah, so, okay. I would argue it's a factory method, but I would not fight over it.
Just to tease you.
I know.
Another comment I'd like to make, if nobody has questions, I don't want to maybe to give you an impression, I wrote a pattern book, or several pattern books actually, and the first one was the second one after the Gang of Four pattern books. So, and I'm teaching that for, I forgot how, maybe 30 years now.
And I think we are allowed to say the title of the book, Patterns-Oriented Architecture, which is a POSA, which is again, a classic. Yeah, this is something that everybody should have taken a look at.
Maybe one comment, I gave a talk ages ago about design patterns in modern C++ and still using inheritance from time to time, but actually using a lot of the customization points through template parameters. And that often turns around the inheritance hierarchy on top down. So what you see, the Golf pattern, you have the base abstraction and then derived classes. If you use template parameters, you tend to have then have the CRTP pattern inside, where you more or less inherit from your parameter instead of going the other way around.
Yeah, good comment.
So maybe I should resurrect that talk for next year.
Why not? I think, as I said in the beginning, I think we are not talking about this enough. We talk about the little details in the language, standards, features, but not so much about how to design things, the big picture. All right, then if an early lunch break, this is good, I believe. Thank you very much.